My name is Isabelle and I am a postdoc in the Earth Observation Data Group at the University of Oxford. And I just want to say thank you for the opportunity to share some of my results today, and also thank you to my co-authors for their contributions. So today I want to talk a little bit about how we can use the infrared atmospheric sounding interferometer, or IASI, to make measurements of volcanic plumes. And I'll largely focus on plumes of sulfur dioxide. So to begin with, I want to talk a little bit about why we monitor volcanic plumes, and then also why we use satellite data to do this, before giving a little bit of an introduction to our IASI retrievals and the IASI instrument itself. And then I want to talk a bit about some of our results from two studies that we're currently doing. The first looking at the eruption of Raikoke, which took place in June 2019. Has been a particularly interesting case study. And then a second study, which has been looking at over a decade of IASI measurements of SO2. So to start with, why do we bother monitoring volcanic plumes? Well, first and foremost, there's the hazard that these plumes present. So local to the volcano, there are hazards that this presents to human health. And then further afield, the potential hazard that these pose to aircraft. So previous encounters of aircraft with volcanic ash have caused considerable damage to planes, and in some cases can lead to engine failure. And so obviously that's a potentially life-threatening circumstance that should be avoided. And so it's important to know the location of these volcanic plumes, particularly ash, in 3 dimensions. These plumes can also cause considerable damage to infrastructure, and then they have a number of different environmental and climatic impacts. And there's a number of different factors which can control the extent of these impacts. For example, the volcano's location, the magnitude of the eruption, and the height of that eruption as well. And in addition to this, making measurements of volcanic plumes, in particular looking at the volcanic gases, can give us some insight into volcanic activity and potentially give us some information on what's happening within the magmatic system itself. So why do we use satellite data? Well, obviously, making measurements on the ground can provide very valuable information on emissions. However, these measurements can be limited. This is often because making these measurements can be expensive, and there are limitations associated with the remoteness of some volcanoes or difficult terrain. So there's a lot of logistical challenges, which means that having a continuous ground-based monitoring network in place, or even just conducting field campaigns, is not always viable. And so using satellite data, we can begin to fill in some of these gaps on monitoring worldwide. And we can get a global perspective of different emission sources from a consistent source. And using satellites, we are also able to track emissions as they move away from the source and travel across the globe and interact with different meteorological systems. And so it gives us a very different perspective of the plume, which can be very valuable, particularly if we're thinking about the hazard to aviation. And so satellite measurements have been used for the last few decades, and these have largely focused on volcanic ash and also sulfur dioxide, although other gases and aerosols have been studied as well. And advances over the last few decades mean that these results are becoming increasingly interesting. Particularly advances in spectral and spatial resolutions of different instruments mean that there's more and more valuable information coming out of satellite results. There's also now a multitude of different instruments in orbit that can be used. There's geostationary instruments that are getting coverage up to every 5 minutes of a disk. And there's also polar orbiting satellites which obtain information sort of a couple of times a day. There's also instruments that are using different parts of the electromagnetic spectrum, so particularly the UV, infrared, and also visible imagery is used. And ideally, we want to use multiple instruments and ground-based data, if it's available as well, to get a full picture of different volcanic plumes. And that's because each of these instruments and each method that's used to extract data has advantages and disadvantages. So I am working with the infrared atmospheric sounding interferometer, or IASI, which is a hyperspectral sensor on the board of 3 meteorological satellites. It's METOP A, B, and C. The first of these instruments was launched in 2006, and data first became available in 2007. And since then, 2 more instruments have been launched, so in 2012 and 2018. And at present, all 3 of these instruments are still orbiting and providing data. So these instruments have circular pixels with roughly 12-kilometer diameter pixels, and that's within sort of this square across the swath. And each of these instruments obtains global coverage twice a day, and that includes a nighttime measurement. So this is one of the advantages of using an infrared instrument like IASI. So very commonly, UV sensors have been used for monitoring emissions of SO2 due to the really great sensitivity within the UV to SO2. But because they're relying on reflected solar radiation, there are gaps at nighttime and during high latitude winters. And so using infrared instruments like IASI can fill in that gap. And it's another reason why it's good to use multiple instruments together. Perhaps IASI's biggest strength is its spectral range and resolution. So it's measuring across the spectrum, the infrared between about 3.6 and 15.5 microns. And it's doing that with a spectral resolution of 0.5 wave numbers. That's a really high spectral resolution. And that means that we're better able to resolve different spectral features within the infrared, and so extract more information about the atmosphere and things within it. Within the IASI spectral range, there is sensitivity to both SO2 and ash. And on this slide here, I'm showing a simulated clean atmospheric spectrum for part of the IASI spectral range. And this is part of the spectral range that we're most interested in. So this is modeled with the fast radiative transfer model RTTOF, which replicates what IASI might see given certain conditions. So in this case, we're using standard atmospheric profile, and we've not put in any layers of cloud or SO2 or ash. And there are a couple of key features. So there's absorption features associated with carbon dioxide, ozone, and water vapor. And if I now overplot a simulated SO2 spectrum, what you can see is actually it's quite hard to tell the difference between this and our clean atmosphere. But if we take the difference between those, it reveals 2 of the 3 SO2 absorption features within the IASI spectral range. The other one is off in this direction at around 4 microns. It's quite a small feature, so we don't use it in our retrievals. Of the 2 that we use, the Ne3 absorption band, which is around 7.3 microns, is the largest absorption feature. And that means that it's very sensitive to SO2 and can be used to make measurements of smaller amounts of SO2. It's also where there's sensitivity to the height of SO2, which is another thing that we want to be able to obtain. It is, however, co-located with this water vapor absorption band, and that means that its use can be limited in cases where there's a lot of water vapor. So that might be, for example, in the Earth's boundary layer, where there is often a large amount of water vapor, which can mask our SO2 signal. In contrast, our Ne1 absorption band at around 8.7 microns is a smaller absorption feature, so it's not quite so sensitive, but because it's located in an atmospheric window, which means we can see right through to the surface, that means there's potential for retrieving information about the SO2 much closer to the surface. And ideally, we want to use both of these absorption bands to obtain as much information about SO2 as possible. So I'm going to overplot an ash spectrum, again simulated with RTTOF. And you can see that this has potential. The absorption is within the Ne1 absorption band, which means there is potential that ash might affect SO2, the SO2 signal. And then characteristic of the ash shape, the ash spectrum is that it's got this kind of V shape between 750 and 1,250 wave numbers. And we can use this part of the spectrum to extract information on volcanic ash, in particular the optical depth and the effective radius of particles. And that means that we can combine those to obtain mass information about volcanic ash. And then we can also use it to get height information as well. For the rest of this talk, I'm going to mostly focus on SO2 because that's what we've been primarily working with in the last year. So we have a number of different techniques developed for IASI which are able to obtain information about SO2. The first of these is our linear retrieval, which was developed by Walker et al. In 2011. And we use this to detect elevated amounts of SO2. And we have an equivalent retrieval for ash as well. And this technique works by representing the spectral background within a covariance matrix. Deviations from this spectral background implies that there's SO2 present, or something else that's not represented in the covariance matrix. And the extent of that deviation can give us some idea of the magnitude of SO2, the amount of SO2. Now, this technique makes a number of assumptions, and for that reason, we don't use it as a quantitative tool, although it can show trends in activity, and we can use it to identify these plumes of SO2. It's using the full spectrum in either the NI1 or the NI3 absorption bands. We tend to use the NI3 absorption band because it's less noisy. And that means that we have increased sensitivity to SO2 compared to if we were using just a single or a couple of channels within the spectral range. But despite using all of these channels, this retrieval is very fast. And that means that we can apply it in near real time, which is really useful, especially if we're thinking about the hazards associated with volcanic plumes and wanting to help aircraft avoid them. It also means that it's quite easy to apply this to a large volume of data and identify plumes that we want to study further. And on the right-hand side here, I'm showing an example of our linear retrieval output from the recent Soufrière eruption, which took place this year in April. And you can see this plume to the east of the volcano over the Atlantic, and then 24 hours later, it spread across the Atlantic and almost reached the west coast of Africa. So once we've identified a plume of interest, we can then use a more quantitative tool to obtain information about these plumes. This was developed by Elisa Carboni. And this technique works by iteratively fitting spectra, the simulated spectra, with our measured spectra. So we use the RT12 model to simulate the SO2 spectra, or a series of SO2 spectra, and then we work out which of these spectra fits the best with the measured one. And we determine how good the fit is with a cost function. And where we've minimized that cost function, we have a good match between the simulation and the measured spectrum, we can extract information about the plume. So namely, we get information on the column amounts, which gives us an idea of the amount of SO2, and then also the height of the plume. And in addition to that, we also generate a comprehensive error matrix. And that's really useful for seeing how good our results are, helping us to interpret them, and also for applying a quality control. So as I said, one of the advantages is that we're obtaining both the altitude and the column amount. But in cases where there's not much height information, we can also fix the height and run it in this other sort of a different mode. And that's particularly useful if we're looking at smaller emissions, and we can base our height on, say, the height of the volcano. So the downside of this retrieval is that it's quite a lot slower, and that means that we rely on our linear retrieval to identify pixels of interest, which we can apply this retrieval to. So before I go on to talk about some of the case studies or some of the work that we've been doing, I wanted to take a little bit of time, or a very small amount of time, to highlight that this isn't the only work that we do in the Earth Observation Data Group. There's also this retrieval scheme called ORAC, which is the Oxford Rail Retrieval of Aerosols and Clouds, which other members of my group work on. That can obtain information on aerosols and clouds and can be applied to volcanic ash. And that's something that Andrew Pratt has been working on. And this is an example of this retrieval applied for volcanic ash for the Raikoke eruption. So these are outputs from Himawari. We've got just a single scene from the 11.2 micron channel. You can see sort of the ash, the signal from the ash to the east of the volcano. And then this is a RGB composite. So again, you can see sort of different structures to the ash cloud. And then these are results from ORAC. So you've got the mass results and the cloud top heights. So I'm not going to talk any further about this, but just wanted to highlight some of the other products that the group is generating. But I'm sure Andy would be happy to talk to anyone if they're interested in these results. So those are examples from Raikoke, and I want to go on and talk about the Raikoke eruption now and our perspective from IASI. And Raikoke is a very remote volcano in the Kuril Islands. You can see its location here, sort of south of Kamchatka. It's an example of where using satellite data is incredibly valuable. It's a very remote volcano, very limited ground-based monitoring in place, but it's also a region where there's a lot of air traffic. So it's a very good place to be using satellite data. And the volcano erupted on the 21st of June in 2019. You can see this pretty amazing image from the International Space Station on the left. This eruption, over the course of several hours, emitted very large quantities of ash and SO2 into the atmosphere. So I said it was a very interesting eruption to study with satellite, or a very useful case study to use satellite data for. But that doesn't mean that it didn't have its challenges. In fact, in many ways, this eruption has been very challenging to study with IASI, and I imagine other instruments too. So you can see on the left here an animation which was produced by Andy. It's true color images from the Himawari satellite. It's a pretty amazing animation showing this plume. But it shows some sort of complex features that we've had to deal with. So first you can see it's over there's a lot of cloud in the background. Just rewinding that, you can see initially that there's multiple small pulses before the main part of the eruption, before we get this sort of sustained plume. And you can also see that there's multiple layers to this plume. So if I again go back, you can see that there's this larger plume, which is quite high, and then there seems to be a sort of consistent emission beneath this as well. So yeah, ash-rich, cloudy, multiple pulses and multi-layered, all combined to make this challenging. And then in addition to that, this was a very large injection of SO2, and the plume persisted for quite a long time, so for several weeks after the eruption. And we've actually made a couple of adaptations to how our retrieval works. Because of this, because it's highlighted a few challenges. It's been a great opportunity to really test our retrievals. And I'll talk a bit about one of those developments in a minute. So to give you an idea of some of our first views of this eruption, on the left here is a snapshot from our old near real-time web page. So this is a group web page which displays the linear retrieval results for SO2 and ash. And you can see the large plume from Raikoke, North of the Pacific, and then also a second plume, which is from the Alawan volcano in Papua New Guinea, which erupted a few days after Raikoke. It's also quite a large eruption. And so this near real-time web page, unfortunately, was taken down towards the end of last year. We're in the process of having it replaced, as it's a really useful resource to be able to go to, and for other people to be able to go to after there's been a big eruption, to see whether we're identifying anything with IASI. So another product that we often generate are these monthly averages of our linear retrieval results. And I use these to sort of demonstrate the full extent of the plume. So you can see in the northern hemisphere, this very large elevated emission associated with Raikoke, so it circulated the entire northern hemisphere above 30 degrees. And then you can see the tracks from the Alawan plume as well. And then we can also look at the linear retrieval results for each day. So we get a morning and evening overpass result. You can see the plume begin to move across the globe. And then a few days later, you get a second plume as well, which we think was a smaller emission from Raikoke. And then we can begin to sort of watch this plume circulate. And you see the second plume from Alawan there, sort of nudging into the plot. You can see that there are bands of SO2 where the column amounts stay really high, and then you get these sort of tendrils circulating the globe. And then two interesting features are these sort of parcels of SO2 where the column amounts stay really high. And we can watch as these move across the globe. So this one here is going to travel northwards and across Canada, and the second blob is going to travel westward and will eventually circulate the whole globe. I don't want to talk too much about these blobs of SO2 now, but they're quite interesting in terms of their dynamics. It seems like they rise in height, and that's something that we're studying further with some collaborators at the Naval Research Laboratory. And I think will be pretty interesting when we finish that study. So yeah, once we've identified interesting plume with our linear retrieval, we can then run our iterative retrieval to obtain more information about these plumes. So I'm showing some results here from the first few days after the eruption. The top line is showing our column amounts, which again gives us an idea of the amount of SO2. And then beneath this is the heights that we're retrieving. And there's a few interesting structures to this plume. So we've roughly divided it into two parts. So the northern part of the plume, in here we've got sort of the core part of the plume where the column amounts that we're retrieving are very high. In some cases they're higher than 400 Dobson units, which really is very high. And the heights here as well are much higher than other parts of the plume, generally between 9 and 18 kilometers. And then there's sort of the southern edge of the plume where we've got lower column amounts, generally less than 100, probably for the most part less than 50. And it's also the lower plume as well, so it's generally less than 5 kilometers. And this is really interesting. I think it's reflecting what I showed earlier in the animation from Himawari, which showed that there were multiple injection heights during this eruption, multiple pulses. And I think what we're seeing is this sort of larger plume, which is emitted much higher, and then this underlying layer associated with this sort of lower plume. And we did a quick check of our results, and this is something we're exploring further. So we're thinking about using the wind direction profiles. So this is from ECMWF Era 5 forecast data. And you can see in this the wind direction or the U and V vector components of the wind direction in the different levels of the atmosphere. So got the U and V vector components, and then the height is shown by the color. We're using the same color bar as for our heights from the IASI retrieval. And we're just trying to use this as a quick way of showing that our results are sensible. So our lower plume here is moving what we think is less than 5 kilometers, and it's moving to the east with a slight southerly direction, which matches fairly well with our ECMWF wind direction for levels for that kind of height. And then for our higher plume, we've got movement to the east and then slight northerly direction, which again corresponds well with ECMWF data. And we're sort of studying at the moment to see how we can use this wind data to get a rough idea of maybe a first guess of the heights of our plumes, and then as a way of just double checking that our retrieval results are sensible. We've also seen results from other studies as well, different satellite instruments and model results, which have a pretty similar heights to what we're attaining with IASI. And then now we have these results on the SO2 amount and the heights, well, we can get an idea of the vertical distribution of SO2. We do that by gridding our results, and we convert our column amounts into a mass, and then we use our heights to look at how it's distributed. What you can see is sort of similar to what I said before. We've got this lower plume, less than 5 kilometers, and then we've got a higher plume as well, between 9 and 15 kilometers generally. And this is sort of around the height of the tropopause and nudging into the stratosphere. And it's really important to understand how these heights relate to the tropopause, because plumes which are higher in the atmosphere are going to have a very different impact and lifetime to plumes which are in the troposphere. And this kind of product is also really useful to provide to people who do dispersion modeling of SO2 and ash. So this helps them know how much SO2 to inject at different levels in the atmosphere. And then they can see how that plume evolves with time. And so we've done some sort of estimates of the total mass. These are daily total masses. We've got a total value of 1.6 teragrams, which we reported on 23rd of June 2019. These are preliminary estimates. As I said before, we're in the process of making a few adaptations to the retrieval, and so it's likely that this may change slightly. So I wanted to sort of talk about how the plume evolves with time. And one of the ways we do this is we take these vertical mass distributions and combine for the entire time period we're looking at. So in this case, we're looking at about 60 days, and we combine them into one plot. So in this plot, we have on the x-axis the days since eruption, on the y-axis the height, and then the color is showing the mass. And the first thing I want to draw your attention to is this sort of layer that appears at 7 kilometers. And this is not volcanic, it's not the true height of the plume. And what's happening here is that as our plume is spinning over time, we're beginning to lose the height information. And that means that the retrieval sort of tends to the a priori height, which we use a default height of 400 millibars, which is around 7 kilometers. So that explains this result. Now, we want to correct for this, because if we place our SO2 too low in the atmosphere, that means that we'll be overestimating the amount of SO2 in the profile. So we've been thinking of ways of doing this. And so what we've done is we've looked at the averaging kernels, which are an output of the retrieval. And so the averaging kernel for height tells us where we have good height information. So a value close to 1 implies that there's a lot of information on the height, and that we can trust these results. Whereas a value close to 0 implies that there isn't very much information on the SO2 height, and that the result is going to tend to the a priori. So this is a map from the 2nd of July, and you can see that we've got the sort of core of the plume, which has a good averaging kernel value. And that means that we can use the information in this to perhaps inform our retrieval. Further away from this, is particularly towards the edges of the plume, we've got a much lower value, and perhaps that's where our results are going to tend to the a priori, and we don't trust them as much. We can look at how this averaging kernel varies over time. So the thick black line here shows the median averaging kernel, and then we've got standard deviation from this represented in blue. We can see that this starts off high and then begins to fall over time. So what we've done is we've made some changes to the way we implement our retrieval. We extract information where we have good height information. So we take the heights from these pixels, and we use this to reset the a priori for the next day that we're studying. And that can give us some improved results. So this is our density plot shown with this new implementation. And we can see our lower plume at the beginning of the eruption here, which lasts for just a few days. Then we can see our higher plume, which is no longer ending up at 7 kilometers. And this plume lasts for several weeks after the eruption took place. And these results are consistent with previous observation that the lifetime of SO2 is very different in the troposphere and in the stratosphere. And another interesting thing that we're seeing is that there's some evidence for plume rise, and that's associated with these sort of parcels of SO2 that I mentioned during the linear retrieval animation, where there's evidence that these are climbing in height. And that's something that we're beginning to explore further, what is driving this. So I want to move on to the next part of my talk, which is going to discuss a bit how a study where we're applying our SO2 retrievals to the entire lifetime of IASI data. So that's from the middle of 2007 to the present. And now we have over a decade of SO2 measurements or SO2 data. It seems like a great opportunity to apply our SO2 retrievals to as much of this data as possible and begin to look at the results. We've been using the Jasmine data analysis facility to do this, and also for our Raikoke study. And this is a really fantastic resource, which has allowed us to do as much processing as we have. And we're hoping that we'll be able to create a data set that we can archive, and then we can make it available to other researchers. And also, but hopefully use this data set to ask some interesting science questions. So a few things to mention before I show you the results are, firstly, there's some gaps in our analysis, so we're still running the retrieval. So we need to fill in some of these results. And also, as I showed with Raikoke, we've come up with a few changes to our retrievals. As I'm sure many people experience, it's always an ongoing process with the retrieval development. So it's likely we'll have a newer version of this data set at some point in the future, which I think will be particularly useful when we're talking about using this sequential a priori, so that we don't always end up with plumes at 7 kilometers when we've run out of information on the height. So we've run the retrievals now from July 2007 to December 2018 with some gaps. And we can generate plots like this now, which show the total mass of SO2 for each day. And in this, you can see the sort of a baseline of 0.05 teragrams associated with smaller eruptions. And then we have spikes in this, which are associated with larger eruptions. So I've labeled a couple of them, some Okmok and Kasatochi, Soufrière Peak, and Nabro, although perhaps some of this is also from Grimsvötn and Puaye, which erupted around the same time, emissions from Holorum and Kalbuko. And that's just a few of them. I have to spend some time in the near future going through this data set and trying to identify all of the different sources, which is a fun challenge. And we've been thinking about different ways of visualizing this data. One of the things that we're interested in is how these emissions vary across the globe, and particularly with latitude, as a volcano which is erupting in the tropics will have a different impact to volcanoes erupting in the poles, and has more potential for moving across, spanning both hemispheres. So what we've done, and I'm showing the results in this plot, is to get an average value for different latitude bands for each day. This plot's quite small, so I just talk through it. We've got results from 2007 through to 2018, which is shown by these different rows. And then across the x-axis, we have the day of the year, and you can see the months marked in this band. And then the color is representing the average log 10 value of the SO2 mass in teragrams. What you should be able to see is that these results are largely dominated by large eruptions during this period. So to zoom in, this is the result for 2011. And in this, we can identify a number of large eruptions, so Grimsvötn, Nabro, Puaye, and then some signal. These all erupted quite close together. And then we've got a strong signal from Naimaragira and Argongo. These volcanoes are quite close together, which means it can be quite difficult to distinguish which one of them is actually emitting without using other resources, so other satellite data or ground-based data. And then we can also look at results for, so an example for 2015, you can see an emission from Calbuco and also from Etna. And because we have information on the height of these plumes as well, we can split up these results into stratospheric and tropospheric. So I'm showing these results here. You see that stratospheric results are in blue. These are largely dominated by these big eruptions. And then, whereas in the troposphere, we've got results from perhaps from smaller emissions. We've still got our sort of signal from these large eruptions, which I think might be related to the results going to the a priori when we didn't have so much information. But we also have these streaks across the plot, which are likely to be due to sort of smaller but maybe more persistent emissions, either volcanic or potentially anthropogenic as well. So just another way of looking at those results, we can take a multi-annual average of them, and we've done that and grouped them into different height levels. So 0 to 5 kilometers, 5 to 10, 10 to 15, and then 15 to 20. And unsurprisingly, these results are quite different for different levels. So close to the surface, so particularly for 0 to 5 kilometers, we can identify a number of different SO2 hotspots. So, for example, over Central and South America is a good example, where we've got some really strong sources of SO2. And most of these are likely to be volcanic. And this is actually a really good region to study with IASI because a lot of these volcanoes are very high. And so they're often outputting the SO2 into above the boundary layer, which makes it much easier for IASI to see. And then we have other signals as well. So you see a strong signal over Iceland and Kamchatka. In Kamchatka, there's frequent large eruptions as well. So actually it persists in all of these multi-annual averages. And we can identify some point sources too. So Kilauea in Hawaii, Etna in Sicily. And not all of these sources are volcanic as well. We've got elevated signal over South Africa, and so signal in Norilsk in Russia. These are likely to be due to power plants. And then we have sort of this band of SO2 running from the Middle East and over China, which again is likely to be an anthropogenic source of SO2. As we move higher in the atmosphere, we lose some of these lower altitude emitters. So we no longer see Hawaii, for example. We can still see some of our very high volcanoes. And then as we move even higher in the atmosphere, we're able to see sort of traces of large eruptions that have taken place. So you can see a sort of elevated signal which is from the Naba eruption or Merapi. In this plot, you can see sort of a slightly elevated signal, which is related to Calbuco. And these are signals which are persisting in the multi-annual averages. And we're beginning to think about the kinds of questions that we may be able to answer with this kind of product. If we think back to one of my earlier slides where I was saying why we bother monitoring volcanic plumes, well, firstly, one of those is the hazard that these plumes present. And there's increasing interest about the effects of SO2 on aircraft as well, particularly sort of long-term exposure, like continual takeoff and landing in areas where there's SO2. And this is something that maybe a data product like this might be able to contribute to. We've got the height information. We also have estimates of the amount of SO2. And then another thing that we're interested in is the environmental and climate impacts of SO2 emissions, which depend a lot on the volcano location, the height of the emissions, as well as the amount. And again, this is something that we might be able to contribute to with a data set like this. And in particular, we're thinking about things like the magnitude of eruptions versus the frequency of eruptions. So how does the impact of a large eruption, which happens only occasionally, differ to the impacts from smaller emissions into the troposphere, which are happening all the time? And this is something that a lot of people have been thinking about perhaps for the last 5 or 10 years. And it's something that we may be able to explore a bit further with data sets like this, although of course it would be important to bring in results from other satellite instruments and ground-based data where it's available. So I want to finish there. Just to summarize, we have numerous products for studying volcanic plumes in the Earth Observation Data Group. Raikoke has been a really fascinating study for a number of reasons and has led to a few changes to our retrieval. And then we've got this longer-term study of the IASI measurements, and which hopefully we'll be able to use to study and look at a number of different interesting science questions. And we're also really hoping to make this data set available to other researchers, and hopefully it'll be useful. And then sort of thinking towards the future, we're really lucky in that we have this really long-term record of SO2 emissions from the IASI satellites because they were launched in 2007. And it's likely that these instruments will be in orbit for a while longer. But also in the next 5 years or so, there's going to be the next generation of IASI instruments as well, which will have higher spectral resolution. And there's also a geostationary instrument, which will a satellite going to be launched, which has an instrument which is similar to IASI. So this opens up new potentials in the future, which is quite exciting. So I think I will finish there, and thank you very much for listening, and I'll try and answer any questions. Thanks.
Wonderful. Thank you so much, Isabelle. I'm going to just change that. So if you do have any questions for Isabelle, put them in the chat now, or I guess in the Q&A box if you really want to, but either way, I'll monitor either. I kind of wanted to start out with a very broad question. I'm an earthquake scientist, so like I know really nothing about atmospheric science or really volcanoes either. But this seems like my mind is blown about how much data you have in terms of like 3D data, the height of the atmosphere across the world, but also like in time as well, moving through time. It's just so much data. And I'm wondering like, how did people monitor SO2 in the atmosphere before this? Like this must have been a radical shift, like a huge leap forward in monitoring things like this. So like what was being done before it, and what does that huge leap forward mean? Like what sort of sciences are looking at this data, and do they even know the full potential? I guess that's a very broad question, but.
Okay, so part A, which I think was what did they do before?
Yeah, let's go with that.
Okay. So there was, I suppose, measurements at individual volcanoes across the world, but it was pretty limited to volcanoes where there's either a lot of interest or they're continuous measurements. And yeah, basically since the satellite era, there's been a huge change in what we're able, like it gives you a global perspective. And it starts slow initially. So you've got mostly a study of these larger eruptions in the 80s and 90s because the satellite technology wasn't quite there. Well, it was impressive, but it's not what we have now. So now we have newer instruments. So IASI is pretty good, but then there's also the UV sensor, so Tropomi, which is perhaps one of the newest instruments, which is very exciting, which has this incredible spatial resolution. So we've gone with the satellite data from being able to study these larger eruptions to now being able to look at smaller emissions, including from like non-eruptive degassing, so things that are happening between these large eruptions, and looking at smaller eruptions as well. So yeah, it's a really incredible change. And I think it's been seen with other types of satellite remote sensing as well. So using the people who use INSAR to make measurements of volcanoes, you've gone from not, knowing that a few the major volcanoes that are erupting to being able to identify unrest at volcanoes, which we previously knew nothing about.
Yeah, cool. Okay, I mean, I have other questions, but there's a question in the chat, so I'll go to that one instead. Okay. So Bob Tubbs is asking, is there any scope for using the GIIRS hyperspectral sounder currently in geostationary orbit over China with hourly data, or is the data quality not good enough?
It's something that we've thought about, but not really had the time to do. And it's the kind of thing which we thought about in relation to this new instruments that will be launched in the next few years, is geostationary version with a sort of hyperspectral sensor on. And so we've kind of had thought about using one of the Chinese satellites to get an idea of whether what we would need to do and how we would implement it. But yeah, we've just not had the opportunity to yet. There's also one slight problem with these geostationary data sets, in that with hourly data, or I think the newer instruments might be every 3 hours, it's just such a huge volume of data that we don't really know how we're going to store it and process it, which should be a fun thing to think about going forward.
Oh my gosh. I mean, it already seems like an overwhelming amount of data.
Mm-hmm. It's quite a lot.
Can you explain, I mean, just for the layman like me, what sort of data is this geostationary orbit? Like why and what is it collecting?
So it's similar to IASI. I'm not so sure about the Chinese satellite, or actually of any of the details of the new satellites as well, but they're measuring, like IASI, across the infrared with a high spectral resolution. So it'll produce a similar spectrum to IASI, which we're able to extract information about SO2, ash, other gases as well, if we're interested in non-volcanic things. I think the new one, which will be over Europe and the Atlantic, isn't going to have the same spectral range as IASI, so we'll have to sort of tailor the retrievals to work for individual parts of the spectrum. So it's quite exciting, but a lot of data.
Oh, Chris, do you have a question? You've just unmuted yourself.
Sure. So yeah, Isabelle, I'm just wondering what is the sort of sensitivity level or the noise level of this IASI data set or method? And also I'm wondering if it like clips at a certain value, if you get like just a super concentration of ash, but I'm more wondering about the low side of it. Like what's the noise level and how does that compare to like how much ash you need to have or SO2 you need to have to cause problems to planes?
So I don't think I can remember any of the numbers for this, but in terms of like the noise in our data set, so I suppose like a detection limit, this is actually quite variable. So in some cases, say higher in the atmosphere, we're able to observe smaller amounts of SO2. Lower down in the atmosphere, we need a larger amount of SO2 to be able to observe or to make a measure, get a good result. For ash, I can't remember the numbers. The more ash there is, the more likely it's to obscure the SO2 signal. So eventually we begin to lose information. So our retrieval has a number of things in it. So we have a cost, which tells us how good the retrieval is. If that value is too high, which is often the case if we have a lot of ash or a lot of cloud, which is obscuring the results, then actually we have like a quality control, which will remove those pixels. So very often that means that we'll obtain a lower estimate of the mass because we've removed potentially the thickest part of the plume which is obscured by ash, but it means that we trust our results a bit better. And yeah, we just sort of acknowledge that, ash is a problem, and that's the case for most satellite instruments as well. I hope that answered the question.
Yeah, thanks.
All right, so if anyone else in the audience has any questions, do put them in the chat. I have just one more. I'm wondering whether meteorologists who study atmospheric effects of other sorts of things in the atmosphere, do they use any of the modeling that you're like, can any of this modeling of SO2 show you things about the atmosphere and how it moves around the world or things like that? I'm not really sure what the question is. I'm just wondering kind of like how all that enormous amount of modeling that you do with how SO2 moves around the world through time, whether that has any applications within these other fields.
I imagine it could do, and that's part of the reason why we're generating such a large data set, is so that we can make that available to other researchers in slightly different areas, but who are still interested in volcanic emissions. So hopefully other people may be able to answer that question.
And so are the results, you said that the website is down at the moment, but are like the modeling results that you showed, do they go online somewhere, or is it like in a separate paper?
We're currently working on it. So I'm working on the paper, and then we may make some slight changes to the retrieval, just so that, but now we've done these other case studies and found improvements. So we might make a change, undecided whether we should just publish version 1 now or make some adaptations first. But yeah, we'll hopefully archive that somewhere and just make it available, hopefully sometime in the near future. And the Neural Time webpage as well, that was a really useful resource, and unfortunately it was just taken down. But I think we're talking with people in COMET about how to get that set up again.
Brilliant.
Yeah.
I guess keep an eye peeled on the COMET information circulars and emails. Brilliant. Well, I think that's probably all the questions.